Alright, okay, so previously when we discussed about electromotive force, okay, we do a little bit of revision. So we look at the example that we, okay, the example that we use. Okay, so let's say that we have a power source. Okay, let's say that we have a power source. Okay, so from what we learned previously, let's say that this power source have a label of 3 volt. So it would mean that this power source is able to do the work of 3 joule to convert 3 joule of chemical energy into 3 joule of electrical energy. So this 3 joule of electrical energy will be supplied to every 1 coulomb of charge. So this is the electromotive force of the power source. So I repeat, if the power source, for example a dry cell, have a label of 3 volt, it will mean that the electromotive force of the dry cell is 3 volt. So what does electromotive force of 3 volt means? It means the power source is able to do the work of 3 joule, convert 3 joule of chemical energy into 3 joule of electrical energy, and this for every 1 coulomb of charge. So every 1 coulomb of charge that come out, every 1 coulomb of charge that come out of the power source carry the energy of 3 joule. Okay, so let's say that this 1 coulomb of charge need to pass through 2 bulbs. And let's say that the 1 coulomb of charge pass through the first bulb, do the work of 1 joule, then that means the potential difference across the first bulb is 1 volt. This is potential difference. The definition for potential difference is work done by 1 coulomb of charge to go from one point to another point in an electric field or in an electric circuit. Okay, so if 1 coulomb pass through this bulb, do the work of 1 joule, then that means the potential difference across the first bulb will be 1 volt. And if that 1 coulomb of charge do the work of 2 joule to overcome the resistance inside bulb number 2, then that means the potential difference across bulb number 2 will be 2 volt. So you see total energy is every 1 coulomb have 3 joules. So you see 1 joule in the first bulb, 2 joule in the second bulb. Okay, so total will be 3 joule. Same with the total amount of energy that the charge carry when the charge come out of the power source. This is in theory lah. However, in reality, this will not be the case. Okay, this will not be the case. In reality, maybe every 1 coulomb of charge that come out of the power source only carry 2.5 joule. Although the label, the EMF is 3 volt, but every 1 coulomb of charge that come out of the dry cell only carry 2.5 joule. So if that is the case, maybe this first bulb, when the charge pass through the first bulb, maybe it will do the work of 1 joule. And then the second one maybe do the work of 1.5 joule. So that means the potential difference across the first bulb will be 1 volt, the second one will be 1.5 volt lah. So total is still correct. 2.5 joule total here, same with the amount of energy that the 1 coulomb of charge have when it come out of the dry cell. So why is it like that? Why is it that the label say 3 volt, but 1 coulomb of charge that come out only have 2.5 joule? The reason is because inside the dry cell you have internal resistance. Very good. You have resistance inside the dry cell. So this is very logical because you see inside the dry cell you have chemical, you have electrolyte, you have electrode and so on. All of those conductor, all of those material will definitely have resistance. So when the charge want to come out from the dry cell, it will need to do work to overcome all that resistance. Alright, so that means this diagram we can redraw again. I draw again so that it looks like this. This symbol represents the total amount of electromotive force, the actual electromotive force of the dry cell. So this resistance symbol symbolizes the internal resistance inside the dry cell. Okay, so like this so I draw dot 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 dot. So this represents the dry cell. So this purple color dot 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 box represent the dry cell represent the battery. Okay so that means the 1 coulomb of charge that come out, 1 coulomb of charge come out actually carry 3 joule. But when the 1 coulomb of charge want to overcome the internal resistance, it did the work of 0.5 joule. Okay, here 0.5 joule. So 1 coulomb of charge that come out of the dry cell only left 2.5 joule Okay, get the idea. So total is still 3 joule Okay, total is still 3 joule, which is the same as the electromotive force of the dry cell. Okay, now when we put the voltmeter, if we connect voltmeter here, this reading will show, yes, 1 volt. When we connect voltmeter here, this reading will show 1.5 volt. And if we connect voltmeter, if we connect voltmeter here, the reading will show 2.5 volt. Very good. Because you see this voltmeter, it connect here, and here it means that it show the reading of the potential difference from here until here, meaning the amount of work done by every 1 coulomb of charge when go from this point to this point. See or not? So from this point to this point, every 1 coulomb of charge do the work of 2.5 joule. So the reading will show 2.5 volt. Okay. However, if I disconnect, listen here, okay, if I disconnect, what will happen? If I disconnect, that means here still got current or not? No more already, right? All of this become no more. No more current. So that means all of this reading will become 0. You see or not? Here becomes 0, here becomes 0. There's no more reading because the charge doesn't flow through the 2 bulb anymore. Okay, so if the charge doesn't flow through the 2 bulb, so where do the charge go? Do the charge can flow or not? Actually still got a little bit of charge can flow. Pass through the voltmeter. Very, very, very extremely small amount of charge can flow. Pass through the voltmeter. Why? Because the total resistance here is extremely high. Why the resistance is very high? Because the resistance of the voltmeter is extremely high. So what happened is when this resistance of the voltmeter is extremely high, what will happen is this voltmeter will get the vast majority of the work done. When the charge come out, pass through the internal resistance and the voltmeter, almost all of the 3 joule will go to the voltmeter because the voltmeter have extremely high resistance. Okay? This is the concept from what you learn about series circuit. If you still remember, in a series circuit, how is it that the voltage is distributed? For example, if this is 3 volt, if this is 1 ohm, then how much is the voltage here? How much is the voltage here? How much potential difference? 1.5 volt, 1.5 volt, because both of them have the same resistance. So it will be divided equally. Okay? And then, if, let's say, I change this bulb, okay, so let's say I change this bulb. This is still 1 ohm, but I change this bulb to become 2 ohm bulb. Then what will happen to the potential difference? Yes, very good. This one will be 1 volt, this one will be 2 volt. What if I change this into 5 ohm? Then what will happen? What happened? 1 ohm, 5 ohm. Then this will be 0.5 volt. This one will be 2.5 volt. You see or not? You see, the voltage is divided according to the ratio of the resistance. You see, this ratio is 1 to 1, right or not? So the voltage also 1 to 1. You see this one 1 to 2, so the voltage also 1 to 2. This one 1 to 5, also 1 to 5. You see or not? Okay? So again, the higher the resistance, it will get more voltage. Why? Very logical. Because if the resistance is higher, that means the charge will need to allocate more of the energy to overcome the higher resistance. So it's very logical that the charge will do more work at the higher resistance. Understand? Get the idea? So the higher resistance bulb will get more energy. So just a little bit of logical question. If like that, bulb number 1 or number 2 will be brighter. Which bulb will be brighter? Yes, the bulb number 2 will be brighter than number 1. Okay, number 1 will become dim. Number 2 will become brighter. Because the energy, more of the energy go towards the bulb number 2. For the situation, for the third situation, 1 ohm, 5 ohm. Get the idea or not? Okay? If 1 ohm, 1 ohm, then both will get the same amount of energy, so both will have the same brightness. Understand? Okay, get the idea? Okay, now remember this concept where if the resistance higher, then it will get more of the energy. Okay, this is very important concept. So we go back to here. So you can understand why is it that the voltmeter will get the vast majority of the 3 joule. That means out of the 3 joule that the charge carry, 2.9999999 joule will go to the voltmeter. So the internal resistance maybe only get 0.00001. So if you look at the reading of the voltmeter, will show 3 volt. Understand? So that means if that is the case where the internal resistance is small, the resistance of the voltmeter very big, then the reading of the voltmeter will show the electromotive force. Meaning, that means, let's say that if you have a dry cell that have no label, let's say you have a dry cell that have no label, you don't know how much is the internal resistance, you also don't know how much is the potential, you also don't know how much is the electromotive force. So the easiest way to measure the electromotive force is straight away take the voltmeter and connect to the dry cell. Then the reading will most probably be the electromotive force. Get the idea? Okay, I repeat. Okay, why like that? Why is it that if you take the voltmeter, connect straight to the dry cell, the reading of the voltmeter will show electromotive force? Because the resistance of the voltmeter is extremely high. So for a normal dry cell, most probably the internal resistance is very low lah. So compare like this resistance very high, so the vast majority of the energy will go to the voltmeter. So the reading of the voltmeter will be, you can say that it's the same as the electromotive force lah, right or not? Right, very easy, right? Just take the voltmeter, connect to the dry cell, then you can know how much is the electromotive force. Right. This is if the internal resistance is very small. It only works this way if the internal resistance is very small. But in this world, we don't only have dry cell, right or not? We have a lot of other kind of power source. We have lead acid accumulator, we have generator, and so on. A lot of different kind of power source. So if we have a lot of different kind of power source, logically, different kind of power source will definitely have different magnitude of internal resistance, right or not? So that means, let's say you have a power source here. Let's say you have a power source that you don't know how much is the internal resistance. Are you willing to bet your life that if you connect the voltmeter straight to the internal straight to the power source, the reading will be equal to the EMF? Are you very confident, absolute confident that you can bet your life? If wrong, you can shoot me, okay? Can or not? Are you confident? You don't have confidence. Why? Because what if the internal resistance is very high? If the internal resistance is very high, then that means the internal resistance will also get a big amount of voltage, right or not? Big amount of potential difference. Then that means the reading of the voltmeter will not be equal to the EMF anymore. If you bet your life, then you have just died, okay? So that means we have to think of a way in order to determine the actual electromotive force without having you bet your life, okay? A very safe way to very confidently find out how much is the electromotive force. So the way that we can do that is through experiment. Okay, so let's look at this activity 3.7 to study the effect of, wrong one. Okay, so look at this one. This is the correct one. Okay, determining the EMF and internal resistance of a dry cell. Experiment 3.5. Okay, this experiment is extremely important because question likes to ask. It can come out in objective also can, structure also can, essay also can. Also, of course, can come out in your practical also can. Okay? This is a very versatile experiment. It can come out in many places. Then you can ask in various amount of ways. So it's very important for you to understand how the concept of this experiment. How is it that we can determine the electromotive force? Okay, now, so you look at this setup of the experiment. Okay, so you have a rheostat connect to the dry cell, and then there is a voltmeter connected across the dry cell. So this reading of voltmeter will show what? What will the reading of the voltmeter show? The reading of the voltmeter will show the potential difference across the rheostat. Right or not? The reading of the voltmeter, this reading is equal to potential difference across rheostat. Meaning, every 1 coulomb of charge pass through the rheostat do how much work? If every 1 coulomb of charge pass through the rheostat do the work of 1 joule, then the reading will show 1 volt lah. If every 1 coulomb of charge pass through rheostat do the work of 2 joule, then the reading will show 2 volt. Okay? Now, you look at this experiment, what we do is, we want to slowly increase the current, and then take the reading of the voltmeter. Basically, we want to look at the relationship between the current and potential difference when the current getting higher and higher. What will happen to the potential difference? Okay. So you see, what happened is, this is the result. You see, as the ammeter reading, that means the current getting bigger, from small to big, what happened is the voltmeter reading go from big to small. Is this normal? This is totally different from what we learned in Ohm's law, right or not? When we learn about the relationship between current and potential difference, it should be directly proportional, right? The higher the current, that means the higher the potential difference, the higher the voltage. But why is it the opposite? You see the current getting bigger, the voltmeter reading getting smaller. So what is going on here? The reason is because, like what I said just now, the reading show the potential difference across rheostat. So how is it that you can make the current become bigger and bigger? You need to decrease the resistance, right or not? You need to adjust the rheostat so that the resistance of the rheostat becomes smaller and smaller. So when the resistance of the rheostat becomes smaller and smaller, the total resistance of the whole circuit will also become smaller and smaller. So when the total resistance becomes smaller and smaller, then the total current inside the circuit will become higher and higher lah, right? Resistance go down, current go up, right? Okay. However, remember, inside the dry cell you have internal resistance. If the resistance outside here becomes smaller and smaller, it will mean that the potential difference across the rheostat will become smaller and smaller. Remember, resistance become lower, then the amount of work done by the charge to overcome the resistance will decrease, right? Because no need to do so much work to overcome the resistance. So that means the amount of energy here at the rheostat will go down. That means the potential difference at the rheostat will go down. So if the energy at the rheostat go down, where do the energy go? Will go to the internal resistance. You see, like this. You look at this situation. You see this 1 ohm, 1 ohm, 1 ohm, no change, right? But the resistance, when the resistance of the second bulb becomes bigger and bigger, you see this amount of voltage become smaller and smaller. Although the resistance doesn't change, but the voltage becomes smaller. This one automatically becomes bigger, this one automatically becomes smaller. So the other way around is also the same. If I decrease the resistance of the second bulb, if the second bulb I change into a bulb with lower and lower resistance, that means the voltage of the first bulb will getting higher and higher, you see or not? Getting from 0.5 to 1, from 1 to 1.5 volt. The voltage of the first bulb will automatically increase. So that is the same case for this situation. When I decrease the resistance of the rheostat, the voltage across the rheostat, or the potential difference across the rheostat, will go to the internal resistance, you see or not? So that means the reading that show the potential difference across the rheostat will decrease. Okay or not? It will become smaller and smaller. Okay, get the idea? So this explains why that the voltmeter reading will become smaller. Okay? If you take the data and plot the graph, this will be the shape of the graph. Okay, this will be the shape of the graph. As the current increase, the potential difference getting smaller and smaller. Remember, this is the potential difference across the rheostat. Okay, this is the potential difference across the rheostat. This is the current that passes through the rheostat. Okay, so you see getting smaller and smaller. Now, we want to find out the electromotive force from this graph. How? How is it that we can find out the electromotive force from this graph? Using the concept just now. Using the concept where if the resistance is higher and higher, then it will get more and more of the energy, right? If the resistance is smaller and smaller, it will get less and less of the energy. So logically, let's say that I can increase the, let's say that I can increase the resistance of the rheostat, slowly increase the resistance of the rheostat. So what will happen is more and more of the potential difference will go to the rheostat, right or not? And when I increase the resistance more and more, the current will become lower and lower, right or not? So follow this trend, follow this route. That means that at one time, I will be able to increase the resistance of rheostat so high. I repeat, that means if I continue to increase the resistance of the rheostat will become high enough that almost all of the energy go to the rheostat. Right or not? If that is the case, then that means the reading will show electromotive force, right? Understand? I repeat. Okay, start from the beginning. If I decrease the resistance of rheostat, the energy will go from rheostat, go to the internal resistance, right? If I don't do the opposite, instead of make the resistance smaller, I make the resistance of the rheostat higher and higher. Then at one point, the resistance will be so high that all of the energy, or almost all of the energy, all of the voltage, go to the rheostat. This reading show the potential difference across the rheostat, right? So if all of the energy go to the rheostat, then that means the reading will show electromotive force. Because all of the voltage, meaning all of the voltage is equal to the electromotive force. If all of the voltage go to the rheostat, then the reading will show the electromotive force. Right? Get the idea? Anybody have any question? Can Okay. So how do we know that the resistance is already high enough that all of the energy go to the rheostat? How do we know? From the current. From the current. You see, if the resistance is super high, if the resistance of the rheostat is super high, what will happen to the current? Super low, right? It will be so low that the current will look like 0. Right? That means when the current is 0, that means the resistance is so high that all of the voltage go to the rheostat. The reading will equal to the EMF. So remember, current 0, reading equal EMF. So we look at the graph. We want to know when the current is 0, how much is the reading? Right? So what we do is we extrapolate the graph. Extrapolate the graph. Extend the graph until it cut the y-intercept, which is the potential difference across the rheostat. So that means at this reading, at here, when the current is 0, that means the resistance of the rheostat is so high that all of the potential difference go to the rheostat. So that means this number 3 is the EMF. You see or not? Okay, can see. So that means the y-intercept of this graph is equal to the electromotive force. Okay? Anybody have any question? Can understand why is it that the y-intercept is equal to the electromotive force? Okay, Okay, now we can also see from this graph the internal resistance is how much? How do we count the internal resistance from this graph? Okay, you see, okay, let's look from here. Let's look at the basic concept. Okay, let's look at the basic concept. Alright, so from the equation of V equal IR, this is the total potential difference. Total potential difference must be equal to the electromotive force, right? All of the potential difference must be equal to the electromotive force. This is the total current that passes through the circuit. How about the total resistance? How to count the total resistance? We must take the resistance outside, or we call it the external resistance. The resistance is this 2 bulb is the external resistance plus the internal resistance. This will be equal to the total resistance in the whole circuit, right? Get the idea? So you see, electromotive force equals to current times resistance, or the total resistance in the whole circuit. V equal IR. Okay, now let's say that we expand. Let's expand this equation. Now we see what is this actually? IR. What is IR? V, right? V is potential difference, right? Potential difference of where? Which part? Potential difference of which part of the circuit? Very good. This you see, If this current is the current that passes through the external resistance, this resistance is the resistance that is outside, right? I repeat, this is external resistance. This is the current that passes through external resistance. So, current that passes through external resistance times resistance of external resistance, then you get potential difference outside the circuit lah. That means outside here. The potential difference outside here. Okay? Current outside here times resistance outside here, you get potential difference outside here. So the potential difference outside here, we represent with the symbol of V. Plus, what is this? Not internal resistance. This is the current that passes through the internal resistance times the internal resistance. V equal IR. If this is internal resistance, this is current that passes through internal resistance, then that means this is the potential difference that is taken by the internal resistance. You see or not? Potential difference at the internal resistance. But we do not have a special symbol for potential difference across the internal resistance. So we just put IR again. Continue with IR. So you see, the potential difference outside of the power source plus the potential difference across the internal resistance. That means the potential difference inside the power source then equal to the EMF lah. Right not? Very logical, right? The EMF will be equal to the potential difference of all the circuit add together. Okay? Get the idea? Okay or not? Okay. So, you see current, this current that passes through internal resistance times the internal resistance, you get the potential difference that passes through the internal resistance. Current that passes through the external resistance times the external resistance, you get the potential difference of the external resistance. And then these two add together, you get the electromotive force. Okay. Remember, okay, now go back to the graph. You see, okay, let's say this value, this 0.5, this is the current that passes through the external resistance. This reading, remember this reading is the potential difference across the rheostat, right? That means this reading, this is the potential difference of the external resistance. That means here to here, this is the potential difference of external resistance. Understand? Can see or not this one? This is the potential difference of the external resistance. So if that is the case, if this is EMF and this is potential difference of external resistance, that means what is this? This must be the potential difference across the internal resistance. You see or not? Here to here, this value, if you take 3, which is the EMF, you minus this value, which is the potential difference of external resistance, then you get the potential difference of internal resistance. And then, what is this value? This is the current that passes through the external resistance, right? But this is also the current that passes through the internal resistance. Because the internal resistance and the external resistance, they are in series. So, the current that passes through the external resistance is of course the same as the current that pass through internal resistance. So that means this is also the current of internal resistance. Okay, get the idea? Okay, so you see from V equal IR, if I want to calculate internal resistance, I use the potential difference that across the internal resistance. I put here, and then I put here the current that pass through internal resistance, then I can get the internal resistance. So that means I take this one, I divide by this, I get the internal resistance. You see or not? I take this value, divide by this value, I get the internal resistance. From the graph, this value divided by this value equal to what? Equal to the gradient of the graph, right or not? This value divided by this value is equal to the gradient of the graph. This means gradient of the graph equal internal resistance. But of course, you need to remember to put negative lah, because this gradient is negative gradient, right? So when you want to calculate, make sure that you remember to put negative, the value of negative first, then only you put in the V over I. Okay, understand? Because resistance cannot be negative value one. Resistance cannot be negative value. Okay, anyway, the gradient of the graph is equal to the internal resistance. Okay, so in summary, if you have an unknown power source, you have a power source that you don't know how much is the EMF, you don't know how much is the internal resistance, you do this experiment, you get this graph, and from the graph you can get the actual EMF and the internal resistance of the power source. Get the idea? Any question? Okay, Okay, let's go back to this equation. You see, this equation, okay, the electromotive force equals to the potential difference of the external resistance. This potential difference of external resistance is also the same as the potential difference that is obtained by the electrical appliance. This potential difference of the internal resistance. Okay. You see, you look at this circuit. When this is disconnected, just now we say that the reading will be equal to the, EMF, right? Because the potential difference is, because the resistance of the voltmeter is very big. So the reading will be equal to the EMF. So which is 3 volt lah. When we connect, when we turn on, the 3 volt reading become 2.5 volt, right now. This is what we discussed just now, right? Off is 3 volt. On, the voltage drop and become 2.5 volt. I repeat, when it's off, the reading is 3 volt, which shows the EMF. When on, the reading of the voltage drop. The voltage drop and show 2.5 volt. The voltage drop by how much? 0.5 volt, right? This is the voltage drop. So this amount 0.5 volt is this one lah, right? 0.5. This is the external potential difference, which is 2.5. EMF is 3, right? So this or this amount of this voltage, we give it a name, which is called voltage drop lah, okay? Because when you on, it drop by this amount. So this is the voltage drop. Okay, so from here, what we learn here is we see that the voltage drop is because of the internal resistance, right? Because the internal resistance takes some of the voltage. So when you on, the internal resistance take more of the voltage, so the voltage drop. But in practical, in reality, the voltage drop not only because of internal resistance, but also because of resistance inside the conductor, inside the wire. Understand or not? So for example, in our, okay, let's say in the switch, you see the switch for the fan and the light is at the back there, right or not? Okay, let's say that the EMF, let's say that at the switch there, the voltage is equal to the EMF, which is 240 volt, right or not? The power supply to our house is 240 volt. Okay? But when you turn on this fan, this is the furthest electrical appliance, the furthest away from the switch. So this fan that is furthest away, can it get 240 or not? No, it will get less than 240. Let's say that it only gets 230 volt. That means short by 10 volt, right or not? That 10 volt is what we call the voltage drop. So this voltage drop gone to where already? Gone to the resistance in the connecting wire. Understand or not? Gone to the resistance in the connecting wire. So the connecting wire from the switch until the fan get 10 volt. And then left 230 volt take by the fan. Can the fan function or not? Yes, because generally electrical appliance can function with a range of voltage from 220 until 240. That is why if you go back home, you look at your electrical appliance, you will see that the label will write 220 until 240 volt. That means if within that range, if the electrical appliance get the voltage within that range, it can still function normally. But let's say that I take this switch, the wire, I connect to a fan in the block D. In block D, so far away, block D. If I turn on, do you think the fan in the block D can get 220 to 240? Most probably cannot lah, because too far away. When too far away, the wire is very long, so the resistance in the wire will be very high. So that means the 240 volt maybe will drop, okay, maybe left, let's say left 200 volt only. 40 volt taken by the wire. That means the voltage drop is 200, that means the voltage drop is 40 volt. So the fan that you connect a wire straight from here to the block D, the fan cannot function because it doesn't get minimum 220 volt. Get the idea? That is the reason why you see in our school, every single block have its own junction box. You see or not? There's a box there. Okay? Inside the box, you have transformer. Okay? So that when the power supply go to the box, then only the transformer convert into 240 and then supply to the whole building. Understand? So every building need to have its own power supply box. If not, let's say if the box is here, one whole school, one box only. If the school is very small, never mind. But for our school, very big, right? Then the wire connect from here until the block that is very far away. Then the block over there the electrical appliance cannot function properly because the voltage has dropped by too much already. Get the idea? Okay. So until here, any questions? Okay, you see there are generally two types of different dry cell, alkaline battery and zinc carbon battery. Okay, so you look at this diagram, no need to study what is the structure inside here. What zinc powder, blah 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 blah, what carbon graphite, blah blah blah, no need to know. In chemistry, I'm not sure whether you got learn all these things or not. But in physics, no need. I just put the diagram just for illustration only lah. Okay, just to let you see only. Okay, so what is the important thing here is you need to know there are two types of dry cell, alkaline battery and zinc carbon. Okay, alkaline and zinc carbon. That is what you need to know. Alkaline and zinc carbon. And then you need to know alkaline, lower internal resistance. Zinc carbon, higher internal resistance. Okay, where is it that we need to use? What is it suitable for? Alkaline battery suitable for high drain devices. Electric toothbrush, toys, portable fan, digital camera, so on. Zinc carbon battery suitable for low drain device, remote control, smoke detector, clock. Okay, you can see the difference between the high drain device and the low drain device, right? You can see the difference, right? The high drain device, you see, okay, like electric toothbrush, you on, and then it moves very fast, wow, a lot of energy. It rotates very fast. The fan, portable fan, okay, very fast one. So all of these use a lot of energy. Okay, low drain device are generally device that you just put there, and then you let it slowly run. Remote control. One day you only press you press less than 1 second, right? That means the amount of time that you use the energy is less than 1 second. You only press, then only got use energy. No press didn't use energy, right? So this is low drain device. Smoke detector, you just put there and then for a few years. Clock, just put there and then let it run slowly run, like that. Okay, so these kind are low drain devices. So but nowadays the zinc carbon battery is very rare. I think no more in the market. There's no more zinc carbon battery. Generally everything is alkaline battery lah. But the problem is alkaline battery, although it's more powerful than the zinc carbon battery, but alkaline battery are generally much more expensive compared to zinc carbon battery. Okay, zinc carbon battery is very very cheap. It's like maybe 20 cents or something like that. You can already buy. Okay, you can already buy 4. Okay, one packet 50 cents. One packet of 4 zinc carbon battery. Okay, sometimes maybe 20 cents already can get last. But nowadays I never see zinc carbon battery anymore lah. Okay. So generally you can use alkaline battery in all the low drain device also, no problem, but it will be a waste of money. Why waste of money? Because before the alkaline battery run out of power, the battery already leaked, already broken already. Understand? That means you waste money lah. You get the idea. So it is only in this kind of sense that we use zinc carbon for low drain device, alkaline battery for high drain device, like that only. Okay, zinc carbon battery definitely cannot be used in high drain device. You just put there. I think the toothbrush you just press, finish already, no more. Okay, get the idea. Okay, okay. So after this, what is it that we want to look at is, okay, electric vehicle and hybrid car battery can be charged using domestic electric supply, charging station or a solar cell charging power station. Okay, so okay, these are, okay, I think you got see this before lah, right? You got see this before in Shell or the Petronas. Okay, Petronas petrol station also have. So this is for charging the electric vehicle, but nowadays it's getting more and more. Okay, because the number of electric vehicle is slowly increasing, but very slowly increasing. Okay, slowly increasing. Because the electric vehicle nowadays is still very expensive. Okay, still very expensive. Okay, so let's look at this one. Okay, just now we learned that if we want to increase the EMF, what we need to do is we need to connect the power source in series, right? So this is what happened. You see, this is a solar cell. This is individual solar cell. 1 solar cell, 2 solar cell, 3 solar cell. So every single solar cell connected in series so that we can increase the voltage. Okay, actually every single solar cell is very small, and the amount of voltage that it can produce is very small. So you need many solar cell connected in series in order to get a bigger voltage. And then after that, if you want to decrease the internal resistance, then you connect all of them in parallel. Then you can decrease the internal resistance. Then you can increase the efficiency of the solar panel. Understand? You can increase the efficiency of the solar panel. Alright, so for example here, you see every single solar panel is 18 volt, 18 volt, 18 volt, 18 volt. So connected, all of them connected in series, you get 72 volt altogether, 72 volt. Okay? And the power, total power that can get is 360 watt. Every single solar panel is 90 watt, 90 watt, 90 watt. Total 360 watt power. Okay. The connection of the power source, whether you want to connect in series or you want to connect in parallel, there is no such thing that say, oh, connect in parallel is better or connect in series is better. There's no such thing. It depends on how you want, it depends on your requirement. If you want the voltage or the total EMF to be high, then connect in series is good But if you want to reduce the internal resistance, then connect in parallel is good Understand? If you want both, you want the internal resistance to be small and you want the EMF to be high, then you need to do both Understand or not? Get the idea. Must connect in series, increase the voltage. After that, many of them connect in parallel again. Connect in parallel, then you can decrease the internal resistance. Okay, any problem, any question?